But there's one problem. Even if all of this makes sense, even if it's super new to many of you, I do have an error. I do have an error. And how can I go about resolving this? Implicit declaration of function square is invalid in C99. C99 means the 1999 version of the language called C. Implicit declaration of function square. Well, it turns out, and I haven't said this explicitly yet, C is kind of dumb. It only does what you tell it to do. And unfortunately, on, whoops, and this is a bug, on line 7, I'm calling the square function by mentioning its name. Unfortunately, on what line of code do I teach the computer that square even exists? Not until a few lines later, line 10 onward. So it's too late. I tried to use square even before it existed. So I could fix this in a couple of ways. I could take this block of code and just move it up here, and then save it again, and run make return. And that works. But that's kind of a cat and mouse game. Eventually, you're going to find when your programs get complicated enough, you can't move like every function above every other function. At some point, you'll construct a scenario where like every function can't be above every other function. But that's OK, because what we could also do is undo this and put square at the bottom and keep main at the top, which is better practice. It's nicer to keep main at the top because that is the default function that the human's going to care about. And I can actually just be a little bit redundant, but it's OK in this case. I can just give the compiler, Clang in this case, a hint as to what's to come. I don't have to tell it how it's implemented, but on line 4, I can use what's called a prototype, a little teaser, like a movie trailer of a function that eventually is going to get implemented. All Clang needs to know from the get-go, though, is what its inputs and its outputs are. The actual implementation between curly braces can come later. So if I now do make return again, now the program seems to compile successfully, and I can do return. And then if I want to type in x is 3, x squared is going to be 9 in this case. And we can do this kind of abstraction in many different contexts by implementing some idea like squaring, thereafter calling it by its name square, but actually not worrying about how it's actually implemented. But unfortunately, we're going to bump up against some limits. We're going to bump up against some limits as follows. Let me go ahead and remind us of a visual you might not have seen inside of your computer, but that's this. In fact, inside of your Mac or PC or laptop or even phones are things like this. Like these are sticks of RAM or memory. When you say my computer has a gigabyte of memory or 2 gigabytes of memory, it's generally got one or more of these things. And they might be slightly different shapes. This, for instance, is from a laptop there. And there's other things inside of your computer which have limits too. But for now, we just care about this. This is a physical device. It stores zeros and ones while your computer is running. When you double click an icon on Mac OS or Windows and you load a program or do some math or write an essay, it is stored in this physical hardware as zeros and ones. Unfortunately, the RAM, the memory you and I have in our computers, is finite. Like this is literally only some number of inches by some number of inches. It literally only stores some number of millions or billions of bits, and that's it. So you have a fixed amount of memory. That's not a good thing when it comes to writing programs that don't know in advance how big the numbers are that the humans are going to type in, or how long of an essay that the human's going to type in. You could certainly contrive a scenario where your essay is just so damn wordy, it does not fit in your computer's memory. Or your number has so many digits, it does not fit inside of your computer's memory because it's fixed. You only have a finite amount. And this has very real implications for 2 problems at least. There's something fairly arcane called integer overflow, and you can actually spot this from time to time in the media as a real-world issue. Here, for instance, are 8 bits. Last time we looked at just 3, but here's 8. And notice this is pretty high number. It's a lot of ones. And this happens, if you do out the math per last time, to represent 254. What happens if I increment this number by 1? Which bit changes based on last time's lesson? Yeah, the rightmost one. The 0 becomes a 1. And then this whole thing becomes all 1s, which happens to be, if you do out the math with the places, 255. If you add one more 1 to this, what's going to happen? Right, in the human world, we'd ideally just get out like a marker or chalk and like write one more number. But in the computer world, if you only have a fixed amount of memory, hopefully it's more than 8 bits. Right? There could be millions or billions. But at some point, you'll run out. And indeed, all of the character or the data types we've talked about today, like int and char and float, literally use a finite number of bits. It's usually 8 or 16 or 32 or 64. It's a power of 2. but it's fixed, which means with a computer program using ints and chars and floats, you can only count so high, even though we humans can theoretically count toward infinity. And the problem is, if you take a number like this that's already as big as it can be with all 1 bits, all the light bulbs on, if you add 1 more to it, and you can't just write down a new one, it's as though all those values suddenly became 0 and your integers overflow. You get to number 255, and guess what comes after 255 if you only have 8 bits? 0, apparently, because all the 1s flip over and become 0. So a computer, therefore, can only count so high using an int, using a float, using a double. And at some point, if you try to add 1 more to it, the number is kind of going to overflow and end up being something you don't expect it to be. Maybe it's positive, maybe it's negative, or maybe it's 0 itself. And we can actually see this. Let me open up one quick program here called Overflow, which is also available online, that literally just does this. If I run it, make overflow /overflow. As I run this program, it's just going to keep counting up from 1 to 2 to 4 to 8 to 16. I simply wrote a program that just doubles the number every iteration of the loop. And I also used another function called sleep, just so that this wouldn't fly by the screen. I wanted to pause, just like in Scratch, you can wait. It's getting bigger and bigger, and this is exponential, so it's going to get bigger and bigger faster, which is nice, because it's not going to take us forever to get to a really big number. But I'm using an int. And with an int, you can only count up to roughly 4 billion, and technically only to 2 billion if you want negative numbers as well, if you want half as many negative and half as many positives. And there it is. Eventually, if I talk long enough, I will double this integer so many times that it just doesn't fit in 32 bits, and the computer notices and has a runtime error, and then weird stuff happens. Now I'm stuck at 0. And so you can actually see this for real. But there's one other issue too, and this is perhaps a super simple program that you wouldn't think has an opportunity for error, but it does. I'm going to go ahead and write a really quick program here, including the standard library, int main void as before. I'm going to go ahead and save this as imprecision, a different problem, .c. And I'm going to simply do this. I'm going to print out, quote unquote, %f\n 1.0 divided by 10.0. Now, based on grade school, what should that answer be? 0.1, right? That's 10%, 0.1. And let me go ahead and run /imprecision. And it's indeed 0.10000, which is the same thing. But I am willing to wager at least like $1 that we've all been lied to, that this 1 divided by 10 is not actually 0.1. Anyone want to go in on this? I should have made that claim before I took out the $. Sorry, I showed my hand. So I make this claim because of the following. Maybe I'm just not looking far enough into the number. You asked earlier how we can show more decimal digits. You know what? Let me see 10 of them. Let me just get some comfort here. Let me recompile the program. Let me rerun it. Losing the $. Let me go ahead and change to like, I don't know, like 55 possible digits. Let's really look deeply into the number. Imprecision. Interesting. So if someone actually played this, I would take the $. Back at this point. And now we see that 1 divided by 10 is not, in fact, 0.10000, like our grade school teachers told us, that those zeros should go out to infinity. It's imprecise. Now, why might this be? Like, why is 1 divided by 10, at least on my Mac or in CS50 IDE here, not actually 0.1? What's the intuition? Well, if you only have a finite amount of this stuff, you can only represent a finite number of numbers, right? If you only have like 32 bits or 64 bits, however many bits you have, you can only permute them in a finite number of ways. Eventually, you run out of patterns of zeros and ones. And it turns out that 1 divided by 10, at least in this computer, cannot be represented precisely because we don't have an infinite number of patterns of zeros and ones to represent all possible real numbers, aka floating point values, because of course there's infinitely many of those and only a finite amount of memory. And to conclude, then, this has very real-world implications as follows. One, if you ever played Lego Star Wars, you might notice, or if you played Lego Star Wars too long, you might notice that the largest number of coins you can collect is 4 billion. And they rounded it a little bit. It's not technically, you can count a little higher, but 4 billion. And that's probably because what data type was Lego using to store the number of coins? integers, which are 32 bits. Meanwhile, that's all fine and good. Like, they actually anticipated that and thought about that. Here is a Boeing 787, or actually, there's a funnier story here. Well, here is a Boeing 787 that actually ended up having documentation associated with it that says you need to reboot your plane every 248 days. Specifically, this Model 787 airplane that has been powered continuously for 248 days, if not rebooted, can lose all of its alternating current electrical power due to the computer simultaneously going into fail-safe mode. This condition is caused by a software counter internal to the computer that will overflow after 248 days of continuous power. So literally, a company like Boeing did not realize that if you leave your plane on long enough and you only use an integer or 32 bits or whatnot, those numbers might creep up big enough that it's going to roll over and have catastrophic consequences, like the plane turning off in this case. And a little less frightening, but nonetheless real, there's one final tale before we wrap up here. And it involves civilization, or Gandhi, in this case here. So if you actually, in the game of Civilization, choose the character Gandhi, who's a very peaceful character by definition in the game, he had an aggressiveness level of just 1, which just means very unaggressive. But the authors of this game, Civilization, only used 8 bits, which means you can only count as high as 255. So 255 would be like a lot of aggression. So 1 is not much aggression at all. But there's a feature in the game whereby if Gandhi, in his Civilization, adopted democracy, there was a line of code that said any time a civilization adopts democracy, decrease their aggressiveness by 2, because they're a content people. Unfortunately, if your aggressiveness level starts at 1 and you subtract 2, just as though you can overflow, you can also underflow, such that 1 minus 2 is not -1. That is actually 255. And so it looped back to the ludicrously high figure of 255, making Gandhi as aggressive as a civilization could possibly be. So there are very real-world design decisions here. And what we will do in the next lecture on Friday and beyond is actually explore these issues, start solving problems with them. Until then, problems that 1 is online, orientation meeting is today and tomorrow. Stick around if you have any one-on-one questions, and we will see you next on Friday.